We talked about the durability using checksums and data placement across the cluster itself. It's not every object as the auditors and replicators go around. What it does, it rolls up portions of objects into these Swift partitions, which have nothing to do with your traditional kind of Linux disk partition stuff. Then there's the concept of a ring. A ring is a consistent hash ring, and it exists throughout the entire cluster, and there's a ring per account server, container server, and for every object. Every storage policy is a ring. So normally, to begin with, you only had 3 rings in Swift, and that meant you had the 3 replica or whatever replica you assigned to it. Today, you can have conceivably as many rings as you want and as many storage policies as you want. And so it's always going to be like 2 account container and then how many storage policies you have for your object. 3 replicas, we've talked about that many times. It's a protection against losing data, right? What a lot of people say is that, well, you know, I don't really care that much about this data, and actually I do have it somewhere else too. This is my backup. I'm totally fine with just having 2 replicas. So you can create a reduced redundancy thing, which is very similar to Amazon's reduced redundancy. Or on the other side of it, we have a customer that had, I think, 18 data centers across the world. Every node or every data center was relatively small in terms of how much data they had. But what they wanted to do is they wanted to make sure they had 1 copy in all of the 18 data centers, for all intents and purposes, creating kind of like a mini CDN inside of their company. So still, it was a tiny cluster, like in terms of data size, but they had 18 replicas. So going back to the 3 replicas, it's just kind of a nice, good, middle of the road. It gives you really, really good durability, like up to the 12 nines that Eric mentioned earlier. MD5 sums, as the data comes in, it gets MD5 summed, checks it back with the client, everything is good. That MD5 sum is also stored in the metadata that someone asked about earlier, which is a standard feature of Swift. It's a kind of a reserved, it's an E tag. That MD5 sum of the object gets stored in the E tag. So if you want to, you can do a head request, which doesn't read any data at all off of the file. It only reads the header data, the metadata, and it returns the E tag. And if, let's say, you wanted to make sure that you did something like, oh, I have this MD5 sum here, should I upload this object? Well, let's check first. Do a post, get the headers back. Oh, it's the same MD5 sum. The E tag has the same MD5 sum as my client. The last comment there, Swift persists object if checksums match. Obviously, you send it in, here's my MD5 sum, and it comes back, and it's the wrong one, redo it. When you build a Swift cluster, you have to create these rings. The rings themselves we'll go into more details about how they actually work and what goes into them. The rings need to be distributed to every single member of the cluster because they are standalone machines, and they need to know what to do even if its neighbor goes down. So it's incredibly important to have a consistent cluster. Let's say you have 100 nodes in your cluster. 1 node goes down, you want to add 10 more. So you compute all these rings, and now you're ready to push them out to the cluster. Now, if you push the rings to the 99 plus 10, but there's one that doesn't actually get it, well, that means that it's not consistent in the cluster. So you have to kind of make sure that you adapt to those conditions. And in our case with Swiftstack, what we do in the interface is we basically tell you, hey, your node is down, can't do that. Fix your node. Or you can simply say take it out of the cluster for now, because it's whatever. It's 1 node out of 100, who cares? We manage that for you. If you run it yourself, kind of like Scott said he was doing a POC with vanilla Swift, you have to figure out a way to actually do that in a way that's graceful and functional. Device list, it puts all the devices in the entire cluster into this ring, and it computes it, and it keeps track of every single disk that's there. The lookup tables is the account container stuff where data goes. How does Swift know where to place data and why? And how do you guarantee that the data doesn't get placed all on one node? If that is that 100th node that goes down, if all the objects were sitting on that node, now it's inaccessible. Swift has this concept called as unique as possible. In the first example up here, those are just 3 disks. So if you have a replica count of 3, it means it's going to try to place the data across those 3 devices. If you expand your cluster to 3 nodes instead, with let's say 3 disks in each, it will try to place the data across the 3 nodes. If you go to, in Scott's example with zones, right, you can create 3 racks like that, and it will try to place the data across the 3 different racks. Why would you have a zone? The whole idea behind Swift was to create something huge that can be operated simply and at the same time provide extreme durability as well as availability. But the cost had to be competitive with something like Amazon S3. So if you have operated kind of standard traditional NASes and SANs, most of you probably have dual switches, redundant switches in every rack. We typically recommend you don't. Why would you when you have 10 racks or 100 racks? In the case of like, oh, you know what, I'm going to put all my Swift nodes in one single rack, so one zone, maybe put your switch, redundant switches on there and then move one out when you go to a next rack. But that's the idea. And then you go to the region, West Coast, East Coast, Europe or something. It's the same thing. It will try to place the data that way. There's one small caveat to that. If you do something like, I think Eric mentioned this earlier, but you have this situation. Let's say you started with 1 node and you had, because you just wanted to do a POC and you bought one with 8 disks in it. And you're like, oh, hey, this will work really well. I'm just going to expand it. So you go to Scott's kind of model and you go, I'm just going to keep this guy because after all, he does hold like 8 times 4 terabytes or something. But I'm going to buy 2 80 disk enclosures down here. Well, that's like a huge disparity in terms of how the data is placed, right? Like, so suddenly you have, whatever, 90% of your data here and 10% here or something like that, or even less actually, 5% here. That's not really going to work with that as unique as possible placement because you can't put 1/3 of your data across 5% in your entire cluster. So Swift is even a little smarter than that, so it will start doing weights of each disk, and it will try to weight the data out across every single disk in the cluster, which means that in some cases you're going to end up with two objects on this enclosure, and then you're going to have 1 object on this and none of that, but some objects are going to be on this one, right? So Swift is kind of working around the as unique as possible based on the weights of each disk. It's not Linux disk partitions. Really what it is directories on disk. The hash ring basically lays out the partitions, directories on disk, and they just look like that if you do an ls on the command line. And there's a set amount of those that you get, depending on what number you happen to plug in into your ring. One example, which is really simplified, is something like this, where you have 8 disks, and you would have 16 partitions per disk that would roll up to an entire cluster partitions of 128. This is what I did for my POC. Now, I'm kind of thinking that this is working pretty well. I'm going to double my capacity, and I'm going to roll it into production. So I buy another one of these. What will happen to the partitions when I add a second node? Instead of 16 partitions per disk, you will end up with 8 partitions per disk, but because you now have 16 disks, this just reverses. You still have 128 partitions in your cluster. It doesn't matter. You kind of want to think about when you start the cluster, how many partitions do you actually want? How big is this cluster going to be when it grows up? And it's better to overshoot than to undershoot. You cannot change the partition power after the fact. Not today, maybe tomorrow. So does the rebalancing stress the network? In the case of what Scott did, immediately, yes, clearly. He called me up and said, we don't have a whole lot of traffic to the cluster other than with the replication, but there's some people, they time out all the time. Okay, let me take a look at that. And then, we figured out that, oh, yeah, because the cluster is actually so busy requesting or returning requests from itself that it times out to the client. So we ended up doing some back-end throttling so that it would go a little slower. What we do is if you have a 4T disk, 4T is not divisible very easily. Like you can do it 4 times and get an integer, and it kind of sucks, right? So we say, okay, well, a 4T disk equals 4,000 gigs, roughly, right? So that's kind of nice to divide by. So we can divide that by some fraction of it and then make sure that we can use the weight of a disk. So we assign the weight of 4 terabytes is now 4,000 of a disk. Now we can, after we format the disk, we can make sure that only 25% partitions that should belong on those 4,000 get, or 25 partitions per hour gets ratcheted up, which turns into about 25 gigs per hour. But it's not guaranteed, right? So what that does on a 4T disk is that it takes a little over a week or so to rebalance a decent cluster with that. So that's something that we do that is a Swiftstack controller feature, and it's something you can do natively in Swift, but you have to keep track of it, and that's what we do for you. We have a backup and recovery function that will let you set up, run your machine. You can have a standby other box that can then be promoted. So if you do that, you can promote that box in probably 15 minutes to take over. So if you're saying like, oh, I want an HA, well, maybe you do, maybe you don't. Because I came originally from kind of a networking and security world, and I've seen firewalls in HA that starts bouncing left and right, and no traffic is going in or out of anything, even though one of them is actually okay, because the other one, because it's flapping back and forth. So I would rather have the situation where you basically click the button and say, you know what, this guy is dead, take over. I don't think we've actually had a single controller outage so far. If you're in the middle of a rebalancing cycle, and you have more rebalancing cycles that the controller is managing for you, the next cycle will not be pushed out because it's down, right? But if there's already rebalancing going on in the cluster, it will continue whether or not the controller is up. It doesn't matter because it still has already gotten its instructions to do what it needs to do. This is kind of the same thing. If you add another disk to your system, here we have 4 partitions on top of these disks. Here we end up with 3 on them. It's simple math. Kind of killed that one, I think. So the ring data structure, it's really just kind of an encyclopedia. Like, what do you do if you have a band 1A, B, C, and you get the word ball? Well, you don't go to the A one, right? You go to the B one, and then you go from there. It's the same thing. It uses the same kind of idea, except for you're going to run out of letters really fast, so we use hashes instead. Those hashes are used for account container and objects across the entire system. And so it's not terribly convenient for a human to read. But there are ways of fixing that. This is an example that's taken directly from a command that's run on a node. And you can run the same command on all the different nodes, and then we'll give the exact same answer. In this case, we see the account, we see that's user 1, we have a container called photos, we have an object, and it's called cloudcat.jpg. And you have the partition number that it's going to live in, and you get a hash of the entire path down like this. So now, like if you have to compare this entire string, it's going to take you a long time, even in computer.
So the hash is computed on the path?
On the entire path, down to the disk. So account, container, and object. In order to not have to compare every single thing in here, even for a computer, take the 3 last, put them up front, makes it easy. Then we take the entire hash, and then you have this number. Anyone know what this number is? That is the timestamp of when this object went in. So instead of calling the object cloudcat.jpg, we call it by its timestamp, which has the fortunate benefit of also giving us another thing other than the MD5. So Swift can now compare the timestamp and the MD5 sum of the ones. And last write always wins. Someone had a question earlier about like what, overriding and stuff, whatever. So that's what it looks like on disk. So we lay down just a convention SRV node. Here's disk number 16. Here's the object. Here's the partition. Here's the sort of 3 last characters of the hash, then the hash itself, and then. So we take that stuff, and then we traverse this ring, and we end up finding the partition, and then we dive deeper into getting the data that we need. And that's how it's then returned back to the client. Here are the 3 things that a ring needs. You need the number of replicas. You can change those. You can set them to 3 to begin with, and then you can go in and change that and recompute the rings, and that's fine. Then you can say number of partitions. Here's where this question comes in. How big is this cluster going to be? You can probably guess double what you think it will be, and you'll be just fine. So if you think that you're going to grow to 50 petabytes, let's pretend you're going to do 100. The rule of thumb is 100 partitions times the number of drives that you think you'll ever have, rounded up to the nearest power of 2, and that will basically create the full partition size of the cluster. The third thing is the min part hours. If we need to rebalance the cluster, if suddenly all those partitions need to be going from one disk to another, it's going to be kind of hard to find where the data actually lives. So we can't just up and vacate them all at the same time. So what this min part hours does is it locks partitions in place for a certain time period, and it will only let one of them move at any given time until it's in place. And it will keep on doing that until it's ready, until it's completely done. So that way, even if you have a replica in flight that you can't find during a read, the other 2 will be available, guaranteed. So that's how that works. And those are the 3 only things. Basically for the Swift stack, well, for Swift in general, you need to compute these rings somewhere. And in the Swift stack case, we do that on the controller, and we ensure that we keep all of those values correct, and we make sure that all of that gets backed up, so that if the controller goes down, we can still recreate those rings. The weights, we talked about that. Weight is assigned to each disk. So if Scott decides that next time around he doesn't want to buy more hardware, he could just go and buy 800 6 terabyte drives, shut down a machine, pull all the drives, push new ones in there, 6 terabyte drives, turn it on, go through the motions, and when he's done all his 10 machines, he will have twice the size of the cluster without any additional infrastructure investment, other than new disks, of course. But that's still cheaper than possibly all the power and the cooling and whatever else that it would come with doubling the cluster. Device location. So this is kind of important, right? Like it kind of goes from the bottom up, so to speak. Disk, also called a device sometimes, up to a node, which is the server and its IP address. And on top of that, the zone I'm talking about. Usually the zone is considered a failure domain. So whatever upstream could fail is sort of how you would assign a zone. That could be power to a rack. It could be a single point of failure switch. It could be anything else. Region is a kind of a physical location. Region kind of implies that you have a certain amount of latency. So in the case of buildings on the same campus, fiber in between, we're talking about sub-millisecond anyway. It's not really called a region, but if they build a data center on the other side of the country, you're going to end up with whatever 50, 100 milliseconds of latency. Now you should be considering that a region, the second data center. Device weights, I think I already covered that. And it's important to know that when you do add these things, the different disks, you can do that either through very laborious commands on the command line. We at Swiftstack do it through our controller, and we basically just multiply every terabyte by 1,000, and that's how we do it. Keep track of that. So this is kind of the end of this module here, and I think Eric will talk about actually what Swiftstack does, which hopefully helps some of you kind of piece together the little things I was talking about. But any questions around this right now? Yep.
What do you mean by the controller? Is that a separate node?
In the case of Swiftstack, managing a Swift cluster, that's what I refer to as the Swiftstack controller. And like when I built my first Swift node, whatever, 3 years ago, I was like playing around. Actually, I had 3 of them, and I'm like going playing around, and I'm generating all the rings off of one node. Well, that's all fine and whatever, but if I actually, and then from there I have to copy out the rings to all the other nodes. Now, if I lose those ring builder files that we were just talking about on that node because I shoot it in the head accidentally because it was on a VM, or the machine gets corrupted, the disk is bad, I'm kind of host. So best practice is to do it on a machine that doesn't actually belong to the cluster, which is why one of the reasons why the controller exists.
What other functions would the controller support for the storage of the cluster?
Everything from managing, monitoring.
Does it act as a proxy as well?
Nope. It's completely out of the data path of the cluster itself. So
And it does all of the calculations for the hashing of the
partitions.
creations of all the hashes.
Yep.
Go into does it maintain the ring, for lack of a better term, database, or excuse me, the ring tables?
Yes.
So that's all done on the controller.
Yes.
All right.
So the requests go to the controller node, is that what it is? What is the front end for me as a client if I want to use
The cluster. If you want to just use the cluster or the data in the cluster, or
yeah.
you speak directly to the cluster. We'll
Write or read?
yeah. You don't ever go through the controller.
So the reason you were saying that the top of rack switch, you only suggest to have one is because of the multi-rack, losing one rack doesn't reduce the capacity that much?
As a distributed model, and at the end of the day, it really turns into statistics, like how much data are you missing, or how much data are you making unavailable by not having something up and running. If you have 100 racks and you lose your top of rack switch, you're going to lose that entire rack. If all racks are equal, you've lost 1% of your entire deployment. If you only have 2 racks, you lose an entire rack and you're 90% full in your cluster, you've lost a lot of accessibility to a lot of data. You haven't lost the data, you've lost accessibility to it. But at the same time, right, if you have 2 racks, you should have at least one object in the other rack. So it's not like, there's some, like, let's say you had to, at that particular moment or during the outage of that rack, that top of rack switch, right, you lose a couple of disks in your entire rack. Well, you probably actually have accessibility issues because you can't reach in the other one. So it's just a statistics game of, like, you have to think through the problem. But your CFO is probably going to tell you that, hey, man, you're kind of chewing up these 10 G switches, top of rack switches, like there's no tomorrow. Like, how many do you need, right? Oh, now you want 2 of them? Oh, that's $20,000. Are you sure you can't do with just one? Really? Right? So, I mean, and that's what Swift was built for at Rackspace. It's like, well, if we only need a 110G top of rack switch in every rack, and we build 100 of them, that's fine.
The calculation will be done for native Swift.
Say again?
The ring calculation, where it will be done for native Swift,
It-
Swift stack.
If you can do it wherever you want. I'm just suggesting that you should not do it on one of the machines in the cluster. You should keep it outside of that and then push the data to the cluster, the configurations. Yeah.
So the controller isn't required, but it is the best practice?
No, so
Because I kind of missed that.
yeah, no, so the
I'm still thinking
the-
like HBAs when we were talking about.
right, no, the controller is a Swiftstack product. That is actually our product. That's what we do. Our CEO used to work on Korea Telecom, Internap, and some other place that I've forgotten, and he built their clusters as part of a team, and it was hellish. And he said, "There's got to be a better way to do this."
So if you were to go and just, the gentleman from Pac-12 mentioned where he went and got native Swift from the.
You can download it from
open
GitHub.
source Swift, you don't get the Swiftstack
Nope.
controller in that environment.
Nope. You have to invent all those things that we do yourself.
Okay.
So authentication, like Scott mentioned, right? Like you get, if you install Swift from the repos at GitHub or from the Ubuntu repos or whatever, right? You get temp-auth. What's
it called?
It's called temp-auth, TEMP auth. It's a placeholder, yeah. It's sort of like, if you look at it and you look at what it does, you're insane deploying that in production. Because it doesn't even do what Swift promises to do for you. Because every time, for example, you update an account in temp-auth, you need to push that out to the proxy nodes, and you have to restart every proxy node. Well, that's not very high availability, is it?
Every time you update the ring tables, you have to push them out and
No, every time you create a temp-auth. If you use a temp-auth authentication mechanism on a whatever cluster that you download from somewhere, or like you download the source code from somewhere and deploy yourself, that authentication mechanism is, for all intents and purposes, not worth anything other than for simply testing that you can put data into the cluster. And that's why we did a lot of work on what we call Swiftstack Auth, which is basically a clone of that, but it is secure, it's fast, and it doesn't require a restart of the proxy servers when we push it out. We also do LDAP and AD.
So when I'm talking Swiftstack as in your organization, that is the controller.
Yes.
But
Well, of course,
Swift ring is
It's a
your
Swi-
product.
the Swift ring that's a core concept of Swift
But the
itself.
controller and all the features. Okay.
Yeah. All those features are what we built to make it easy to actually manage clusters.
Yeah, the light bulb just went on.
Good. We like that. We've had customers who've had their, like the motherboard blow up for whatever reason, so they get a new motherboard under warranty and they pop it in, and just because the motherboard blows, it doesn't mean that the data on the disks were bad, right? So if they do it fast enough, like all of the data hasn't had a chance to move over, so it'll just move some data over, they replace it, and then you do another push config, and then suddenly like data's coming back onto the node again. So it's it depends on what it is. If you literally have forklift going into your data center and shoving its forks right into the machine, and you're like, well, probably not going to save data off of that one. You pull this stuff out and put a new node in and add it, and you're good to go.